So the next part of the discussion here is reactivity series. Reactivity series. When you go for reactivity series, you can see that suppose metal, if you go for the reactivity series, reactivity of metal depends on the reducing power of other metal oxides or metals. Metal salts. So here for example, if we take reactivity series lithium, sodium, potassium, then you can take lead, zinc, hydrogen, then silver, iron, and so on. So this is, you can take this as reference non-metal electrode, reference non-metal electrode, and these are metal electrodes. And here what you are noticing is, that is, for example, if you take lithium, sodium, potassium, highly reactive metal electrodes. Here you can take lead and zinc in particular, moderately reactive metal electrodes. Moderately reactive metal electrodes. If you take silver and iron, least reactive metal electrodes. So we have three different types of metal electrodes: least reactive metal electrodes, moderately reactive metal electrodes, we have least reactive metal electrodes, moderately reactive metal electrodes, and highly reactive metal electrodes. So for example, if that is the case, if you make a comparison between the zinc and silver, for example, if you take reactivity between zinc and silver. So zinc solid plus silver chloride aqueous will give you zinc chloride aqueous plus silver. Silver is going to become the precipitate. Similarly, if you make a comparison between silver and iron, or if you make a comparison between that is zinc and iron, if you take zinc and iron, if you take zinc plus FeCl3, zinc solid plus FeCl3 aqueous, you can say that here it forms zinc chloride aqueous plus iron. This is greenish color. Zinc ferric chloride is greenish brown, you can say greenish brown color, and this is greenish color. So that means here zinc is able to reduce the ferric chloride to iron. Here in FeCl3 iron is +3 oxidation state, and here iron is 0. So zinc is acting as a reducing agent. So therefore decreasing order of reactivity among metals, if you take decreasing order of reactivity among metals. If we take downward arrow represents decreasing, so you can just take here, that is lead is more, so for example lithium is more reactive than, is more better reducing agent than sodium, is more better reducing agent than lead, is more better reducing agent than zinc, is more better reducing agent than silver, and finally it is iron. So this is the decreasing order of reactivity among metals in the reactivity series. So the next part of the discussion here is, that is points to remember in metals and non-metals. Points to remember in metals and non-metals. Here if we take, that is lead and mercury, lead and mercury are poor conductors of electricity. Silver and copper are good conductors of electricity. Silver and copper are good conductors of electricity. When mixing of metals in equimolar proportions to improve in properties like that is heat resistant, anti-corrosion, then anti-corrosion or rusting, etc. Are simply called alloys. Example of alloys. If we take, that is A, brass, the composition of brass is copper plus zinc, and B, bronze, copper plus tin. If you are taking brass, it is used in that is in the manufacture of, that is utensils, then machinery, and so on. Then if you go for bronze, if you take statues, medals, casts and molds. Both these are, that is heat proof and anti rusting. They are long lasting. Then similarly, if you go for that is silver attacked by sulfur to form Ag2S, which is black color, which we call it as tarnishing. which we called as tarnishing. Coating of zinc over surface of iron containers, we call it as galvanizing. We call it as galvanizing. We call it as galvanizing. Similarly, if you go for, that is if you are going for, that is points to remember, if you add few more points to remember, what are the products obtained when you subject Al2O3 to electrolysis? Products obtained when Al2O3 is subjected to electrolysis, that is at anode we get fluorine gas, and at cathode we get aluminum solid. So the continuation here in the points to remember here, in the extraction of metals, we can say that is all pyrite ores are roasted. All pyrite ores are roasted. Example: zinc sulfide, zinc blend. When treated with oxygen, it forms zinc oxide plus sulfur dioxide gas. Then all carbonate ores are calcinated. Example, we can take ZnCO3. This is calamine. Upon heating, it gives zinc oxide solid plus carbon dioxide gas. Zinc oxide solid plus carbon dioxide gas. So if you go to the extraction of metals, extraction of highly electropositive metals, like examples sodium, magnesium. The process is electrolysis. In the electrolysis, we can take electrolytes. If you take sodium chloride fused or sodium chloride aqueous, that is brine solution. So here, if sodium chloride, if NaCl fused is subjected to electrolysis, it gives sodium solid at cathode electrode and chlorine gas at anode electrode. On the other hand, if you go for NaCl aqueous, when subjected to electrolysis, it gives NaOH aqueous plus H2 gas at cathode and chlorine gas at anode. So here what you can expect is, this is called a side reaction. If you go for a side reaction, if you are going for a side reaction, NaOH aqueous plus chlorine gas that is cold, under cold conditions it gives NaClO plus NaCl plus H2O. Here you can take 2, the reaction is balanced, sodium hypochlorite. Chlorite is the product. This is in the case of cold. Again, NaOH plus chlorine gas, this is aqueous. In the hot condition, you can take NaClO3 plus NaCl plus H2O, aqueous. This is 6, this is 3, this is 5, and this is 3. Sodium chlorate is the product obtained. So under 2 different conditions, the sodium chlorate which is obtained, the sodium hydroxide which is obtained at cathode during the electrolysis of aqueous brine, this sodium hydroxide in turn there is a chance for it to come in contact with the chlorine gas. When sodium hydroxide is also called caustic soda in the form of NaOH, when it comes in contact with the chlorine. So NaOH in the cold condition, when it is coming in contact with the chlorine, the reaction takes place. Sodium hydroxide in the cold condition, dilute condition, it reacts with chlorine to give sodium hypochlorite, sodium chloride and water. Same sodium hydroxide under hot condition or concentrated, when it comes in contact with the chlorine, it gives sodium chlorate plus sodium chloride and water. So these are the 2 important side chain reactions. So the next point here which you have to remember is gold and platinum. Gold and platinum are the 2 metals which occur in free state. 2 metals which occur in free state. All ores are minerals, but all minerals need not be ores. Actually, you all know that ore is a compound from where the metals are profitably extracted, but sometimes from the minerals you cannot extract. From the minerals, extraction of metals is difficult, so we have to adopt special methods to extract the metals from the minerals. That's why we say all ores are minerals, but all minerals need not be ores. The metal oxide when dissolved in water, it changes red litmus to blue. What could be this metal oxide? This metal oxide could be what kind of metal oxide? So this metal oxide should be, this metal oxides are basic in nature, because only the metal oxides which are basic in nature can convert the red litmus paper to blue. So example you can take, that is, if sodium oxide is a metal oxide solid dissolved in water, liquid, it gives NaOH. Aqueous, it's a base, it's an alkali, or it's a base. Bases always changes red litmus to blue litmus color. So that means only metal oxides can change red litmus to blue litmus. Suppose if the metal oxide if you're going with non-metal oxide, non-metal oxide when dissolved in water, it is changing blue litmus to blue to red litmus. What oxide it could be? I can say that all non-metal oxides, they are acidic in nature. They are acidic in nature because if you take here, say you are taking chlorine, example you take Cl2O7 chlorine heptoxide, which is a non-metal oxide, it gives HClO4 perchloric acid. It changes the blue litmus to red litmus color. Blue litmus to red litmus color. It's a non-metal oxide. Perchloric acid changes to blue litmus color solution to red litmus color solution. So the next point to remember here is that is sodium when mixed with mercury, it forms sodium amalgam. This is sodium amalgam. It forms amalgam mixture. This is one point which you have to remember. Gold, silver and platinum, they are used in jewelry. Since these three elements are noble metals, they are less reactive under ordinary conditions. Here, if you take for example gold, originality is tested by aqua regia, by a reagent called aqua regia, that is 3 parts of HCl and 1 part of nitric acid. This is the reagent we use for testing the original gold from the fake gold. So the next point here is that is food containers are coated with the tin but not with zinc. Here reactivity, the reason is because reactivity of zinc is more than tin, and here tin forms, Sn is nothing but tin forms a protective layer, and it prevents the food from getting oxidized. The food is oxidized, antioxidants are used. Antioxidants are added to prevent oxidation of food. In particular. So the next point to remember is that is go for Cinnabar. Cinnabar upon heating gives product, that is Cinnabar is HGS. HGS is Cinnabar, It is treated with oxygen, solid, gas, subjected to roasting. First it forms mercuric oxide with the evolution of sulfur dioxide gas. So here to balance the equation, I think if you could take 2 over here and if you could take 2 over here, the number of sulfurs are 2. So take 2 over here and take 3 over here. These are the molar coefficients, and take this mercuric oxide. Again in turn it reacts with the mercuric sulfide, solid. This is also solid, undergoes self reduction, and it gives back mercury, that is liquid, plus sulfur dioxide gas is obtained. So to balance the equation, I think if you are going to take 2 over here, I think and if you take 3 over here, I think the reaction is going to get balanced. So this is called self reduction of the cinnabar, and in the first stage it is undergoing roasting, and in the second stage it is undergoing reduction. So here the next point to be remembered here is all ionic compounds have high melting point and boiling point. High melting point and boiling point. The reason is it is due to strong electrostatic force of attraction between two oppositely charged ions. Example, we can take here NaCl aqueous can give you 2 ions, Na plus and Cl minus ion. So if it is Cl minus ion is an anion and Na plus is a cation. So you can see the strong electrostatic force of attraction. In the ionic molecule. This is strong electrostatic force of attraction, ESFA. Electrostatic force of attraction, strong electrostatic force of attraction. Go for MgCl2. Aqueous. Yes, it gives magnesium 2 plus. It gives 2 positive charges and it gives 1 Cl minus ion. Plus if you take, so you can see the strong electrostatic force of attraction between the one magnesium bivalent cation and two anionic chloride anions. So the strong electrostatic force of attraction operating in MgCl2 also, strong electrostatic force of attraction operates. Strong electrostatic force of attraction operates between the two oppositely charged ions. That's why we can say that melting point and boiling point for ionic compounds are very high. So the last point in the points to remember, that is corrosion in copper. If you take copper solid, it comes in contact with carbon dioxide gas plus water liquid. This is moisture. So you can see here it develops cupric carbonate. It can give, and it can evolve even hydrogen gas. This is greenish blue flakes on metal pipes. Greenish blue flakes on metal pipes. this is nothing but the corrosion which is taking place in copper. I think the reaction is also balanced because there is one carbon and one carbon, 3 oxygens. We have 3 oxygens, 2 hydrogens, and we have 2 hydrogens, 1 copper and 1 copper. Of course, this is again a solid. Going back to reactivity, if we take between sodium, potassium, rubidium and cesium. Cesium is highly electropositive. Metal. Sodium less electropositive metal relatively. And here for cesium, if we take cesium in particular, it is solubility. If you go for solubility, even if you go for solubility also, solubility, cesium hydroxide, you take cesium hydroxide and you take sodium hydroxide, you find cesium hydroxide is more soluble than sodium hydroxide because lattice energy for cesium is less, lattice energy for cesium is less than that is sodium, because the reason is sodium atomic radius of sodium is less, and here the atomic radius of cesium is higher. So therefore the valence electrons which are present in the cesium can be easily lost, and very little amount of energy is enough to break the bonds between cesium and cesium hydroxide and sodium hydroxide. That is cesium hydroxide, suppose if you take very easily less energy, that is cesium ion can be formed most readily than the sodium cation. If you take NaOH, Na plus OH minus ion, so the readiness with which the Na plus ion is formed, the readiness with which the cesium ion is formed is much faster than the readiness with which the Na plus ion is formed, because here the lattice energy, less lattice, here it is greater lattice energy, sorry, this is greater lattice energy, and this is lesser lattice energy is required, lesser lattice energy is required.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.